Alright, so in section 1.5 we want to start looking at what systems that we call homogeneous. And as you can see here, a homogeneous system is a system where the right hand sides are all zeros, right? So there you go, there's your system, all equal to zeros. Now we've seen those before. We should mention first of all that if you've got a homogeneous system, that its matrix equation will look like that, right? This is the zero vector, and so it's going to be A, which is the coefficient matrix, times X, which is the variable matrix, equals column vector equals the zero column vector. And the very first thing you need to look at and understand is that if you have an homogeneous system, automatically 0, 0, 0, which we call the trivial solution, is a solution, right? If x1 is 0, x2 is 0, and x3 is 0, then we have a solution to the system. So every single homogeneous system automatically has a solution. The question then is no longer, is it inconsistent, meaning does it have no solutions? But the question is, does it just have a single solution, or does it have an infinite number of solutions? Is the trivial solution the only unique solution, or does it have an infinite number of solutions? So those are the only two cases that we can consider. Working with homogeneous systems and solving them is just like solving any other system. What you want to do is you of course want to find the RREF, the reduced echelon form of the matrix. And so of course in our case here we have as a matrix (1, -2, 3, 0, -2, -3, oops. Let's try that again. 1, -2, 3, 0, -2, -3, -4, 0, and 2, -4, 9, 0. And this is going to reduce, its RREF, I've already calculated this one, will look like this in this particular case. Now we already know that it's going to be consistent, so I'm not going to get that weird row of zeros and then a non-zero thing. This one in particular reduces to this, which if we write it a little bit, it's the identity matrix. That's this piece, I sub 3. So the identity matrix is the matrix where you have ones down the diagonal, zeros everywhere else, and then right next to it is of course the zero matrix, or zero column vector. So that's just another way of writing this right there. But what we know is, because there are no free variables, right, this column's got or I should say this row's got a leading term in it, this column's got a leading term in it, this column's got a leading term in it, and this column's got a leading term in it. So no free variables, therefore there's a single solution. We already knew what it was. All that we've done is verify that it's the only solution, and so we know that the solution, is going to be x1, x2, x3 equals the trivial solution 0, 0, 0. So it has a unique solution. So working with homogeneous equations, you automatically don't have to worry about inconsistent systems. You can just all you need to worry about is if it's a single solution or an infinite number of solutions. Alright, let's look at another homogeneous system. Here we go. Here is the augmented matrix for another homogeneous system. And so let's run this through and reduce it. And the RREF of this looks like this. And so right there we see that we have a free variable right here. right? X sub 3 is free. That column does not have a leading term in it. Here's a leading term and here's a leading term. So x1 and x2 are basic variables. So that's going to have a free variable in it. We know that when a system has a free variable in it, then that means there's going to be an infinite number of solutions. So we can start by start with x sub 3 and just call it s. And then working on the top row, it tells us x sub 1 minus s equals 0, or x sub 1 equals s as well. And then finally the second row says x sub 2 minus s equals 0, or x sub 2 equals s. So we have kind of a unique situation where it's x1, x2, and x3. So that's the parametric equation for the solution set of this system. It has an infinite number of solutions. Pick your S and you're good to go. We can say this: if we're dealing with a homogeneous solution, the only time it will have a non-trivial solution is if there is a free variable, right? This is an example, because we know it has a solution 0, 0, 0. Here we have a free variable. That means we've got an infinite number of solutions. If we don't have any free variables, then 0, 0, 0 is the only solution. Now, we want to take this same system, and I'm going to change it a little bit. I think we've covered that idea of homogeneous systems pretty good here. But let me take this and let's look at it again. I'm going to change it. I'm going to change it so that it's not a homogeneous system. So we're going to change this right-hand column. So this is a brand new problem, and it's going to have this as its augmented matrix. So brand new problem. I mean, in the sense that we've got a new right-hand side. Okay, so this is going to then reduce. Notice how nice it is to just use technology to do our reduction. RREF into this matrix: 1, 0, negative 1, 7, 0, 1, negative 1, negative 1. Okay, so there we go. And again, we notice leading variable, or leading term, leading term, and no leading term, so this is free. It's not a homogeneous system, right? We had a non-zero right-hand side. So we're kind of back to the original kinds of systems that we were dealing with. But I want us to look at the solution set to this. So we'll finish this out. Now, we can start. We'll kind of keep it a little more orderly here. X sub 3 is S, right? That's our free variable. X sub 1 is going to be S plus 7 if you look across and work on that top row, and then X sub 2 is going to be S minus 1. Now we've learned that we could write this parametrically like this. So the X solution is going to be 1, 1, 1 times S. That's this column, right? And then plus 7, negative 1, 0. Okay, so that would be the formula that gives us the solution set to this system. All right, now here's what I want you to notice. I'm going to flash us back to the previous problem, and just note this, that in the previous problem this was the same and these were all zeros. So we had the same left-hand sides of the equation, but we were dealing with the homogeneous version. So let's just go back and look. So there we go. Notice those are all the same, right? That's what we had, and we've got a solution equal to 0. But look at our solution. Our solution is SSS, or if we wanted to write that in parametric form, it would be 1, 1, 1 times S. And we've seen that before, right? So now go back to the current problem. When you solve a non-homogeneous system, you're going to get, number one, the terms that have parameters on them are actually going to be solutions to the homogeneous system, the homogeneous version of that system. All right, so this is a solution to the homogeneous system. Now this, if we check it real quick, we're going to see that it's actually a solution to that system. Now remember, this system has an infinite number of solutions, but the 7 minus 1, 0 is a solution to that system. So that's going to give us, that's how every one of these, whenever we solve a system of equations, and we'll talk in the non-homogeneous case, whenever you solve a system of equations, you're going to get, the final answer will consist of the parametric pieces that are solutions to the homogeneous version of the system, and the things that don't have a variable, the non-parametric things, are just solutions to the regular system, to the non-homogeneous system.